Here, and in the previous video we left off by talking about the definition of cross product, and namely we saw that the cross product takes in two vectors and it spits out another vector, right? So it spits out x, y, and z, and then we learn how to numerically calculate the cross product as well as the geometrical interpretation. And once again, I'm going to repeat it once again, that you need to know both pictures, right? Both the numerical and geometrical understanding in order to be good at vectors. So we saw that so we saw that with the cross product, and we saw the visualization as well over here, right, of what the cross product means, and we learned about the right hand rule for the sign convention of the cross product. Okay, so in this video we'll be talking about why the utility of the cross product in calculating certain quantities. So as with the previous video, as with the dot product video also, I said that why the definition of cross and dot product is defined as such because these are particularly useful quantities in the study of vectors. They can be used to find the lengths, distances to a particular line, and so on. And sure enough, you can define your own product and call it your own name, right? But the question is, would that quantity be useful in calculating something that the dot and cross product or existing methods cannot calculate? So back to the topic of cross product, the first application of cross product is going to be in the calculation of the area of parallelograms. So if you have two vectors A and B, I'm just going to draw them on a 2D plane now, but they are in fact vectors in 3D. It's just I can't draw in 3D space, so we're going to have to settle for 2D visualizations. So if you have the vectors of A and B, then imagine the parallelogram spanned by them like this. So you bring the B vector, you kind of bring it over, keeping it parallel to the B, and then this side is parallel to this. Okay, so just a parallelogram. Then what is the area of this parallelogram? So let's call the parallelogram A. What's the area of A is going to be, right? It's just going to be length of A times the length of B sine theta. And why is that so? It's because it's actually just base times height. So this is going to be the height of the parallelogram, which is B sine theta, where theta is the angle between A and B. Then since the height is this, then it's just base times height. Yeah. So and since we've learned in the previous video that the definition of A cross B, the geometrical definition, is the length of A times the length of B sine theta n hat, right? Then imagine what happens when we take the length of both sides. So both sides of this equation are vectors, but what if we take the length? Then the length of the right hand side, the length of n hat is just 1 because it's a unit vector denoted by the n hat, the hat, right? The hat tells you it's the unit vector. And so the right hand side is just going to be this AB sine theta, and that is precisely the area of the parallelogram. So another way to express it is to write it as magnitude of A cross B. So you can see the utility of this geometrical picture is this geometrical picture is that if we know the numerical values for A and B, we compute the cross product using the numerical rule, right? And then we can take the length of it, which is using Pythagoras theorem, and we can calculate the area of A just like that. You can see that on the right hand side, the final formula here, we can do it completely numerically, whereas this one, we don't really know what the angle between them is unless we compute it. So yeah, that's the value of the cross product. You can use it to calculate the area of a parallelogram. So okay, second application, right, is closely related to the first actually. So if we have two vectors and we want to find the area spanned by the area of the triangle, right, like this, then this is actually just half of the parallelogram. So it's just imagine the parallelogram, the area of triangle is just half of the area of the parallelogram, which is half the magnitude of A cross B. So that's the second application that I can think of, right? Third application, these are simply more simple applications. We'll talk about how they are useful in defining lines and planes in the next few videos. But the third application is is in calculating the perpendicular distance from a point onto a line. So let's say I have a vector A and I have a vector B. Okay, so let's say this is the origin, and let's say this is point B. And what if I want to find the perpendicular distance from B onto OA? What is the perpendicular distance? Is the distance when you draw a line like this and it's parallel. So this distance is known as the perpendicular distance, and it's also sometimes the closest distance, right? I'll just call this D. Right, it's also the closest distance from the point B onto the line OA, and we'll see more example. We'll see that this closest distance is a common question that they like to test in exams. So the closest distance D is equals to magnitude of B, right, sine theta. And if we refer to if we recall that the A cross B is equals to magnitude of A, magnitude of B, sine theta, n hat, right? Then if we take the magnitude of both sides, then this n hat disappears and this is a scalar, right? It's a real number. Then we can rearrange it by bringing A over, and so we can express the shortest distance as the magnitude of the cross product divided by the length of A. So in so doing, right, actually it's similar to the parallelogram calculation, just that we're dividing by the base. So in so doing, we have found a formula for the closest distance from a point onto a line if we simply know the directional vector of the line, which is A, as well as the position vector of the point, which is B. So just like that, we have calculated the closest distance from a point onto a line. And you'll see more of this when we talk about lines, planes, and so on. Okay, so if that's it, then that's it for this video. In next lesson, we'll be learning about miscellaneous things that we did not cover previously. Okay, so that's all. Have a nice day. Bye.